Hello viewers, welcome to my channel. I'm Hasham Ali Khan. Last two problems are left on this simplex method. So in this video again one problem, how to convert the primal into dual and solving the dual. That's what we have done in the last video also. And remember, this simplex method requires a lot of practice. Simply watching the video, listening the lecture is not sufficient. Along with that, the same problem you have to do it yourself independently. Then only you can be able to get the command. By practice, you become perfect on this topic. Because the simplex method is time consuming and also requires a lot of manipulation of numbers. So you have to be perfect. Now, before starting the 14th problem, I expect my viewers to have a printout of the problems which I have given in the link under my description. So see the 14th problem. Solve the following linear programming problem by simplex method after converting primal to dual. That means primal problem is given, we have to convert it into dual and then dual has to be solved. The primal problem is minimization. The dual problem will become maximization. So minimize z is equal to 1.5x1 plus 2.5x2. Actually in our calculations it is not suitable to take point. Instead of 1.5 we can take 3 by 2. 3 by 2 or 1.5 means same. But by taking 3 by 2 our calculations will become simple. So we'll convert that 3.5 is equal to, 1.5 is equal to 3 by 2. Similarly 2.5x2. So instead of writing 2.5 we can take 5 by 2. Then subject to constraints x1 plus 3x2 greater than equal to 3 and x1 plus x2 greater than equal to 2 and x1 x2 greater than equal to 0. This is the primal problem. Now see carefully here. The primal problem 1.5x1 plus 2.5x2 minimize. x1 plus 3x2 greater than equal to 3. x1 plus x2 greater than equal to 2 and x1 x2 greater than equal to 0. Now we convert into dual problem. So dual problem objective function, instead of minimization we write it maximization, opposite. Then coefficient of objective function of dual are the restrictions of primal problem. What are the restrictions of primal problem? 3 and 2. So we will take 3y1 plus 2y2. Instead of x1 and x2 we are taking y1, y2 because x1, x2 already it is there in the primal. Now subject to constraint. The coefficient of constraint will remain same. The only thing is horizontal will become vertical, vertical will become horizontal. So here 1x1, here also 1x1. This 1 and 1 is in vertical. Now we write it in horizontal. y1 plus y2. Right? Here greater than equal to, so we make it less than equal to. And the restriction are the coefficient of objective function of primal. So what is the objective function coefficient here? 1.5. So 1.5 can be written as 3 by 2. Right? The coefficient of x2 is 2.5. So 2.5 can be written as 5 by 2. And y1 and y2 are greater than equal to 0. So we have converted the primal into dual. Now adding the slack variable, because we have maximization type and all the constraints are less than equal to. In every problem I told you, whenever the inequality is less than equal to, we have to add the slack variable to convert the inequality into equation. So here adding slack variable, the standard form of LPP will be maximize. So 3y1 plus 2y2 plus 0 into s1 plus 0 into s2. S1 and S2 are the slack variable. Now subject to constraints, y1 plus y2 plus S1 is equal to 3 by 2. Then 3y1 plus y2 plus S2 is equal to 5 by 2. And y1, y2, S1, S2 greater than equal to 0. That's all. This is the standard form of LPP. Now an initial solution is taken by taking y1 is equal to 0 and y2 is equal to 0. When we take y1 0, y2 0, s1 will become 3 by 2 and s2 will become 5 by 2. Right? Now first simplex table, no need of any calculations, only coefficients will take. CJ, coefficient of objective function. The coefficient of objective function y1 is 3, y2 is 2. y1 3, y2 2, and s1 0, s2 0. Here also s1 0, s2 0. So Cj values are there in the column and also in row. Basic variable are s1 3 by 2 and s2 5 by 2. Now the coefficient of constraints will be taken in this body of this table. The first constraint y1 plus y2. So 1 y1 and 1 y2 plus s1. s1 is 1. Here 0. Secondly 3 y1. Here 3. Then y2. 1 y2. Then s2 is equal to 1. 0. That's all. Now zj value. Multiply the cj with the variable. 0 into 3 by 2. 0. Plus 0 into 5 by 2. 0. When anything is multiplied by 0, you will get 0. Similarly, 0 into 1, 0. Plus 0 into 3, 0. So all the zj values will get zeros. Right? Now cj minus zj. This is the index row. So cj is on the top first line and zj here. 3 minus 0, 3. 2 minus 0, 2. 0 minus 0 is 0. 0 minus 0, 0. After this, write the optimality test. And for maximization problem, this is a maximization problem. For maximization problem, all the index row elements, this is the index row. This is index row. All the index row elements should be zeros and negatives. Already in the previous problems I told you, all the values should be zeros and negative. There should not be any positive. If there is positive, we have to go for another table. We have to improve the table. The highest positive should be selected. Here 2 positive values we have. The highest positive is 3. So we select this 3. So these are intersectional element and y1. So in the next table, y1 will enter. y1 will enter. Now which will depart? It depends on minimum ratio. 3 by 2 divided by 1. 3 by 2 divided by 1 is 3 by 2 only. That is equal to 1.5. Here 5 by 2 divided by 3. 5 by 2 divided by 3. So we can write 5 by 2 into 3 by 1 will become 1 by 3. That is equal to 5 by 2. 3 is a 6. So 5 by 6. So 5 by 6 will become 5 divided by 6 will become 0.5 divided by 6. 0.833. Now minimum ratio. Whichever is minimum, that will be the outgoing variable or departing variable. Here first variable 1.5, second variable 0.83. So 0.83 is lower. For which variable? For S2. So in the next table what will happen? S2 will depart and Y1 will enter. So here I am writing Y1 enters and S2 departs. Y1 enters and S2 departs. S1 will remain same. Instead of S2, Y1 will enter. This is 0 and Y1 coefficient is 3. That's it. Now we need to write the variables, the values of entering variable. The values of entering variable. Values of entering variable is equal to values of departing variable divided by intersectional element. Already every problem we have done. So what are the values of the departing variable? 5 by 2. Then we have 3, 1, 3, 1, 0, 1. These are the values of the departing variable divided by intersectional element is 3. So 5 by 2 divided by 3 by 1. 3 by 1 means into 1 by 3. If it is division and if we want to make it multiplication, 3 by 1 will become 1 by 3. So 5 divided by 2, 3 is a 6. 5 by 6. 3 divided by 3, 1. 1 divided by 3, 1 by 3, 0 by 3, 0, 1 by 3. So these are the values of the entering variable. Entering variable is y1. So 5 by 6, 1, 1 by 3, 0, 1 by 3. These are the values of the entering variable. Now we need the values of S1. So how to find out values of S1? Value of S1 is equal to old S1 minus intersectional element minus values of entering variable. Already every problem we have applied this formula, right? Old values of S1 are 3 by 2, 1, 1, 1, 0. These are the old values of S1 minus intersectional element of S1 is 1, 1 into values of the entering variable are 5 by 6, then 1, then 1 by 3, 0 and 1 by 3. Now we have to simplify, calculate. 3 by 2 minus 1 into 5 by 6 is 5 by 6. So LCM will be 6. 2 how many times cut 6? 3 times. 2 3s are 6, 3 3s are 9. 6 how many times cut set? 6 one time. 1 5s are 5. So it will become 9 minus 5 is 4 by 6 or 2 by 3. 1 minus 1, 0. 1 minus 1 by 3. 1 minus 1 by 3 is 3 LCM. 3 ones are 3. Minus 1, 2 by 3. 1 minus 1 by 3 is 2 by 3. 1 minus 0, 1. 0 minus 1 by 3. So minus 1 by 3. So what are the values of S1 we got? First one 2 by 3. Then next one is 0. Next one is 2 by 3. Next one 1. Last one minus 1 by 3. So we got the values of S1. Now Zj value. Multiply Cj with solution value. 0 into 2 by 3 is 0. 3 into 5 by 6. So 5 3 is a 15. 15 by 6. Here 0 into 0 is 0. 3 ones are 3. Here 0 into 2 by 3 is 0. Plus 3 into 1 by 3. So 3 3 will get cancelled. 1 remains. 3 by 3. 1. So 0 0. Here it is 0. 3 by 3 is 1. Now 3 minus 3 is 0. 2 minus 1 is 1. 0 minus 0 0. 0 minus 1 is minus 1. Optimality test says all the index row elements should be zeros and negative. But we are getting one positive value. So again, this is not an optimum solution. One more table is required because this is positive. So in the next table, y2 will enter. Y2 will enter. Now which will depart? Now it depends on minimum ratio. So solution value divided by intersection element. 2 by 3 divided by 2 by 3 is equal to 1. Here it is 5 by 6 divided by 1 by 3. So we can write like this. 5 by 6 into 1 by 3 will become 3 by 1. 5 3s are 15 by 6. Or we can say 3 5s are 15, 3 2s are 6, 5 by 2. So minimum 1 or 5 by 2, whichever is less. 1 is less because 5 by 2 is nothing but 2.5. So this is 1. So 1 is lower. So S1 will depart. In the next table, Y2 will enter. Y2 enters and S1 departs. This table. So Y2, here S1 is departing. In place of S1, I am taking Y2 and this Y1 will remain same. So Y2 coefficient is 2. Y1 coefficient is 3. That's all. Now again we have to find out the values of the entering variable. As usual, how we have done in the previous table. Now, values of entering variable. Entering variable is y2. is equal to values of departing variable divided by intersectional element. Which is a departing one? S1. So S1 values are 2 by 3, 0, 2 by 3, 1, minus 1 by 3. These are the values of the departing variable divided by intersectional element. Which is the intersectional element? 2 by 3. 2 by 3. Now see here. 2 by 3 divided by 2 by 3. It will be equal to 1. 0 divided by 2 by 3 is 0. 2 by 3 divided by 2 by 3 is 1. 1 divided by 2 by 3. So we can write 1 by 1 into 3 by 2 is equal to 3 by 2. Here 2 by 3 will become 3 by 2 if we multiply. Right? Similarly, minus 1 by 3 into 2 by 3 will become 3 by 2. So 3 will get cancelled, minus 1 by 2. So these are the values of the entering variable. Which is the entering variable? Y2. So Y2 values are 1, 0, 1, 3 by 2 and last one minus 1 by 2. That's all. So we got the values of Y2. Now we need the values of Y1. So old values of Y1 are 5 by 6, 1, 1 by 3, 0 and 1 by 3. These are the old values of Y1 minus intersectional element. Which is the intersectional element here? 1 by 3. One by 3 is the intersectional element. Into values of the entering variable. Entering variable are 1, 0, then 1, then 3 by 2 and lastly minus 1 by 2. So how it will become? Now see here. 5 by 6 minus 1 by 3. If you take LCM 3, 6 one time, 1 5 is a 5. 3 2 times, 2 1 is a 2. So 5 minus 2 is 3. 3 by 6 or 1 by 2. 3 1 is a 3, 3 2 is a 6. 1 minus 0 is 1. 1 by 3 minus 1 by 3, 0. 0 minus this 3 will get cancelled. So 1 by 2 minus 1 by 2. Here 1 by 3 minus into minus will become plus and 1 divided by 3 2 is a 6. So LCM is 6. 3 how many times cut 6? 2 times. 2 1s are 2. 6 how many times cut 6? 1 time. 1 1s are 1. That is equal to 3 by 6 is equal to 1 by 2. So these are the values of Y1. So 1 by 2. Then we have 1, 0, minus 1 by 2 and lastly 1 by 2. That's all. Now we need to calculate ZJ value. 2 1s are 2 plus 3 into 1 by 2, 3 by 2. So LCM is 2. 1 how many times? 2 times. 2 2s are 4. 2 how many times? 1 time. 1 3 is a 3. So 4 5 6 7 by 2. Here 2 into 0 is 0. 3 1s are 3. 2 1s are 2. 3 into 0 is 0. 2. Here 2 3 is 6 by 2. 6 by 2 plus into minus will be minus. 3 into 1 by 2 is 3 by 2. LCM 6 minus 3 is 3. So 3 by 2. It is equal to 3 by 2. Here 2 into minus half is minus 2 1s are 2 by 2. Minus 2 by 2. 2 1s are 2. Minus 2 by 2 plus 3 by 2. Plus 3 by 2. LCM is 2 minus 2 plus 3. So 3 minus 2 is 1 by 2. So here it comes 1 by 2. Now find out the CJ minus ZJ. 3 minus 3, 0. 2 minus 2, 0. 0 minus 3 by 2 is minus 3 by 2. 0 minus 1 by 2 is minus 1 by 2. That's all. So index row elements. Here all the index row elements are zeros and negative. So we reached the optimum solution. Index optimality test says for maximization problem, all the index row elements should be zeros and negatives. We got zeros and negative. There is no positive. So we reached the optimum solution. No further simplex tables are required. This is the final, right? So what is the solution? The final simplex table says y1 is equal to solution of dual. Solution of dual is y1 is equal to 1 by 2. y2 is equal to 1. And maximum z is equal to 7 by 2. 7 by 2. That's all. And one more thing I told you, it is asking you to find out the solution of dual, and we've got the solution of dual. But the speciality of this simplex method is automatically we can get the solution of primal also. The solution of primal. The solution of primal is under the column slack variable S1 and S2 in index row. This is the index row, these are the slack variable. So minus 3 by 2 and minus 1 by 2. Ignore the signs. Ignore the sign, minus or plus, we are not concerned. 3 by 2. So solution is x1 is equal to 3 by 2 and x2 is equal to 1 by 2. And minimum z. Original problem was minimum. Minimum z is equal to 7 by 2. That's it. Finished. So this is the end of problem number 14. So one more problem, last and final, 15th problem is left. Inshallah, we'll do it in the next video. That will be the end of this simplex method.